So the basis of polynomial multiplication is really thinking about breaking down numbers, and that might seem a little bit odd, but it's really important to understanding how polynomial multiplication works. So if we think about the number 256, it can be broken down into three parts: the 200, the hundreds parts, the tens parts, and the ones part. So we've got 200 plus 50 plus 7. So if we wanted to break down a number, let's say like 354, we can also break it down into something like it's 3 base 10 parts. So there's the 300 part, there's the 50 part, and then there's the 4 part. And you should be able to tell quickly that this is 354. So as odd as that sounds, this really is where polynomial multiplication comes in, is understanding that. So we're first going to do an example where we break down these two numbers. So if I think about 244, that's 200 plus 40 plus 4, and 23 has a 20s part and a 10s plus 3. And I can break this down and multiply it as though I'm multiplying length times width. And so when I'm multiplying for a square, I think of length times width, where one side is the length and the other side is the width. And so when I go to multiply these things, we want to make the side lengths, those things, in the most simple way possible. So a 20 space and a 3 place. So the length of this side from here to here is 23. And similarly, on the other side, we want each part 200 is this segment, 40 would be the length of that segment, and 4. So that makes our multiplication easier. When I'm thinking about multiplying 20 times 200, well, 2 times 2 is 4, so we'll add the 4. And then there are 3 zeros, so 20 times 200 is 4,000. 3 times 20, 3 times 2 is 6, and we've got the 2 zeros, so 0, 0. 3 times 4 is 12, and 1 0, and 3 times 4 is just 12. Again, 20 times 40, 2 times 4 is 8, and then there are 2 zeros. 2 times 4 is 8, and there's 1 0 this time. So this way, when we go to add things together, we've got 4,000 plus 600 plus 800 plus 120 plus 80 plus 12. And when we add these all together, I've got 2, 8, 9, 10, 11, carry the 1, and 1 plus 6, 7, 8, 16, carry the 1, 4, and 5. So this total area, if I multiply 244 times 23, is 5,612. So this is going to make a lot more sense in just a moment, but multiplying numbers in this way makes it a lot more simple without having to remember, oh, do I carry the 1 or do I have a 0 placeholder from our standard multiplication algorithm. So if I have the polynomial 2x to the power of 3 plus x plus 3, we can break that down into the sum, or sum being addition. If I can spell that right, of 2x cubed plus 0x squared. Notice there's a missing 2x squared there. There's a missing x squared, and a single x, and then a 3. How could we break up the number x squared plus 2? How does that polynomial break down? Take a moment, pause the video, and think about that. Okay, hopefully you've had a chance to do that, but hopefully we see x squared plus, there are 0 x's because there's no x value, plus 2. Notice that it goes from a second order, first order, 0 order polynomial. So why is this useful? Well, we can break down any polynomial into its elemental part. So here I've got x plus 3. We're going to make that the length x and 3. And then the height of this is going to be 4. And so when I find the area, I'm looking for, when I'm multiplying these things, I'm looking for the area of this box. So this side length is length x, and this side length is length 4. So all together, the total area of this is 4 times x, because we're thinking about it as a really small rectangle. And if this side has length 3 and this side has length 4, because 4 over here, the same length of a rectangle, this right here would be 3 times 4 is 12. So the total, if I take 4 times x plus 3, is 4x plus 12. And that's kind of our new way of thinking about this. As much as I love the distributive method, 4 times x and 4 times 3, that only gets us so far. And you'll see that in one of the examples coming up. So when I have something like x squared plus 2, remember that there's a missing piece there. I'm going to make one of the lengths x squared and one of the lengths 2, because x squared plus 2, and then the other side x and then 1, and notice we can just add them together. So I think about what's 2 times, or excuse me, I'm going to think about this very orderly. X squared is the first box here. I want to fill in this box. So this length has a length of x squared, and this length has a length of x. So x by x squared ends up being x to the power of 3, because we're finding the area. 2 and x would be 2 times x. X squared times 1 is just 1x squared. And 2 times 1 is just 2. So if we're thinking about this, how do I find the area of all of the insides? Well, I add up all the insides. So if I had x squared plus 2 times x plus 1, that ends up being, I'm adding up all of these things in here. So x cubed plus x squared plus 2x plus 2. And I like to do it in descending order. So x cubed plus x squared plus 2x plus 2. And this would be our final answer when we multiply those polynomials together. Try this one on your own. I'm going to give you pause the video and take about a minute to try this out. We would be multiplying, this would be the problem, x plus 8 times x plus 7. And try and see if you can fill in these spaces. Pause the video. Hopefully you've had a chance to pause the video. This is length x. Length x, we fill in x squared. 8 times x is 8x. X times 7 is 7x. And 8 times 7 is 56. And then here we have to combine like terms. So notice that these two values, they're the same order. So we've got an x and we've got an x to the power of 1. So we can combine those. So 8 plus 7 gets us 15. And we will, let me change cursors. We've got 15x. We've got an x squared. And we're adding these all together. And we've got a 56. And so when I multiply these two binomials, I get this trinomial of x squared plus 15x plus 56. So I want you to think about this. How does this compare to the original question we asked at the video? Well, we're breaking down x into its elemental part, 8 into the ones place. Let's dig into a couple more complicated examples. So this is a trinomial, x squared plus 3x plus 1 times x squared minus 5x plus 2. This is a trinomial, and this is where this method really pays off, because we don't have to do quite as many operations as the distributive property, which could get really confusing. So all we're going to do is assign each side length a piece of this, and we've got our other side length over here. The tricky part about this is this negative 5x, so I'll talk a little bit more about that when we get closer. So I'm just going to assign x squared, 3x, and 1, and then we're going to do the other side of x squared. It's a minus 5x, so we're going to tag that on, and it's going to be a negative 5x that we're adding together, and then a 2, a positive 2. So pause the video, try and fill this out, and I'm going to keep going, but I want you to pause the video and try filling this out on your own. It's really valuable to get these, as many of these as you can by yourself, just to get some practice. Okay, you might notice a pattern here, and I want to really focus on that pattern. When we look at these diagonals, we're looking at the diagonal values. What do you notice here? They're all kind of like terms, and so if we want to think about this, and I'll use my handy dandy highlighter to think about this, those are all together. These values are all together. These values all are x squares. These values all are x's. And these values are all 1s. So notice that we can go around the circle. I've got an x to the power of 4. And here I start thinking, oh, negative 5x cubed plus 3x cubed. Well, minus 5 plus 3 is negative 2. So we've got negative 2x to the power of 3. And here I think 2x squared minus 15x squared plus x, well, negative 15 plus 2 is negative 13, negative 12. Negative 12. When we add those numbers together, negative 12x squared. And then 6x minus 5x ends up being just 1x. Just got one of those guys, and then a 2. And so all we have to do now is add these numbers that we have around the outside to figure out the answer to this big problem at the top. So the answer to the big problem at the top, I'm just copying these down now. As we go around, they end up being, from greatest to smallest, x to the power of 4 minus 2x to the power of 3 minus 12x squared plus 1x plus 2. And we've done this really complicated problem that would have taken us a lot of work otherwise, and we've broken it down. And I think this is a pretty straightforward way. This would be our answer if we were looking for just a final answer. I know this video has gone on for quite a long time, but I want to give you a couple of extra examples, so I'll just talk through these. I'm going to put these values around the outside, and it's a negative 2. All of these are pluses, plus 1, plus 3x, minus 2. We see they're on the outside, so we've got x to the power of 4. Notice that when we multiply, the power goes up. So 3x to the power of 3, because we have the x and the x squared, just an x squared. Negative 2x squared. We've got negative 2 times 3 is 6, so 6x. And then we've got negative 2. Notice this time, however, that these diagonals don't line up the same way that my last one did. And that's intentional. If you notice that that works, awesome. And if it doesn't work, that's okay. It sometimes happens. So I've got this block is the same, is the only one of its kind. The square block is similar to the square block. The cube block is one of a kind. The X block is one of a kind, and the singletons block. So it looks like we can't combine a lot, but we can combine the squares. So I'm going to do it from descending order. So my largest value is x to the power of 4. My next largest value is 3x to the power of 3. My next largest exponent, negative 2x plus x, is negative x squared. Negative 6x, and then negative 2. So this would be our final answer to this problem. This looks kind of complicated, but check it out. The next example is going to break it down. Some things might happen that are kind of interesting. So if I'm looking at this really big problem, I'm a little bit nervous that I'm going to get this really long answer, but this is actually kind of cool because we get this really surprising answer at the end. So I'm going to do exactly what we did, x, and then negative 1, and then I'm going to add these around the corners. X cubed plus x squared plus x plus 1. And then I'm going to start filling these out, and hopefully we catch a pattern here. See if you can catch the pattern. Sorry, I made a mistake. See if you can catch the pattern before I do, before I mention it. X to the power of 5, negative x to the power of 4. X to the power of 4, negative x to the power of 3. X to the power of 3, negative x to the power of 2. X to the power of 2, negative x, x, and negative 1. Did you see it? Do you see, notice our diagonals are really nice because they line up perfectly. And this doesn't always happen. Remember, this doesn't always happen. But they end up canceling each other out. So I'm left with x to the power of 5. Oops, sorry, I'll change my color here. X to the power of 5. Well, I'm thinking about this. X to the power of 4 minus x to the power of 4 is just 0. And again, x to the power of 3 minus x to the power of 3 is 0. And x squared minus x squared is 0. And x minus x is 0. And I'm left with down here a negative 1. So this big cojones of a problem ends up being really straightforward. It's x to the 5th minus 1. And I think that's kind of cool. Thanks for watching this video. I hope this helps you with multiplication. You should have seen some patterns. If you didn't, I know this is a really long video, but go through and check out the patterns that you see. There's lots and lots and lots and lots and lots of really interesting patterns in this. And this is really going to help when we come to polynomial division. Thanks for watching and spending your time. Hopefully you'll learn something new.